high order finite elements is actually not much different from low order finite elements. It's a method where there is like the least barrier between a low order method and high order method, because the only difference is to choose the space a little bit differently. Okay, so for example, what I'm giving here as an example is the one-dimensional equation. Let's stick to Poisson's equation again, and instead of piecewise linear and continuous functions like that, what if we change this requirement to piecewise quadratic and continuous functions like that? Okay, by allowing the functions to be quadratic, I can show that the analysis is what we are going to be doing in the next lecture on the error analysis, but like we can show in the next lecture that we can improve the order of accuracy by upgrading from piecewise linear to piecewise quadratic. Basically, we have more expressive power with piecewise quadratic functions, right? So think of a arbitrary function. Let's say we have a true solution, and imagine we can actually get the most accurate solution possible. What is the most accurate solution possible we can do with piecewise linear functions? It's actually not much. So for example, I'm just giving a very intuitive view of the area estimation we are going to do next lecture. So let's say we have a quadratic function. This is our quadratic function over the element. What is the best we can do? So ux, so this is my u of x. What is the best I can do with a linear function over that piece? What do you think the best linear approximation is going to be? Anybody wants to take a guess and draw it? Would you like to take a guess what is the best linear approximation is?
Straight line to the middle.
It's a straight line in the middle, right? Last time we discussed on if we pull a bunch of elastic springs over and see what is the best solution possible, it's like this, right? Now, what is the discrepancy between the linear function, the best linear function, and the quadratic? It's proportional to what? So let's say we are minimizing the L infinity norm, which is we are trying to minimize the maximum discrepancy, and that makes this to be the same as this, right? The error is equal to, I mean, let's say this is the width of this is h, and we have a quadratic where the second derivative is constant. Okay, so let's work it out. Okay, let's work it out. So from the lowest point to highest point, the distance is how much? The x distance is half h, right? Okay, and now this function starting from here is a quadratic function, right? So let's say here is x naught, and the e of x is some constant times x minus x naught squared, right? And what is that constant given the quadrature of this function? Let's say we have a u prime prime. Should I divide by something or multiply by something? I need to divide by 2, exactly right. So I need to divide by 2 so that I get the same quadrature. Okay, so now at this point, what is x minus x naught? It's half h, right? So e is going to be oh, sorry, I'm not writing e of x, I'm writing u of x is equal to this plus u of x naught. Okay, so in particular, u at x naught plus half h, which is the right side of this, is equal to half of u double prime times half h squared plus ux naught. So I have a distance of u double prime h squared over 8 difference between this point and this point. And the maximum error is half of that height, which gives me u prime h squared over 16. But the key point is the error is proportional to h squared, right? The error of the best approximation using linear functions, assuming my finite element is all powerful to get me actually the best approximation in my solution, then it's still only h squared. That is limited by the expressive power of piecewise linear functions. If I upgrade to piecewise quadratic functions, I can make this error proportional to h cubed. So that's the motivation of going higher order, to make a function, to make my space of functions to be more powerful in representing smooth. Stick to the piecewise continuous and quadratic functions. Let's go from the beginning to the end of finite element method. So we have a weak form of a partial differential equation with particular boundary conditions. Does that change? Okay, we have the same bilinear functional and linear functional. The next step is to restrict the space into the lower dimensional space, into the finite dimensional space. The space changed, but the form of the weak form still doesn't change anyway, right? And then the next step is to take that bilinear functional equal to linear functional weak form and say that equation only needs to be enforced when the test function is equal to the basis. So here comes the question: what is the basis of that piecewise quadratic and continuous functions? Let's go to the simplest example of only one element, so from 0 to 1, a single element. What is the basis of continuous and it's no longer need to be continuous, I only have one element. What is the basis of quadratic functions within that element? Parabola is a general function, not a basis. Somebody give me, so how many, so first of all, how many functions do we need to form a basis?
3 basis functions.
We need 3 basis functions. Why do you think so?
You have a constant, you have x, you have x.
Right, because if we have a second order polynomial, there are 3 terms in the second order polynomials, right? Constant, linear, and quadratic terms. And the constant, linear, quadratic terms are naturally a basis for quadratic polynomials. So I can choose a basis function that phi1 equal to 1, okay, phi2 equal to x, and phi3 equal to x squared. That's a perfectly fine basis. All right. Okay, that works for this element, and it has nothing to do with being continuous across the elements. So now, how about we have 2 elements? Can we use the same set of basis functions for each element? Not anymore, right? Because they don't satisfy continuity. Only this one satisfies continuity. So the question is, we already have a good basis function for the piecewise linear functions. Can we somehow enrich the basis functions, add some more functions to form a basis of piecewise quadratic functions? Yes? How do we do that?
Well, like you construct basis function by like a combination, a linear combination of both terms.
Yeah, good point. We do linear combination of these terms, and in particular, remember what are the basis function we have before. In the linear, in the piecewise linear case, we have a function that looks like this, right? we have a function that looks like this, and we have a third function that looks like that, and this is value of 1. Now we need to add some more functions. What can we do? We need to add functions that makes them quadratic. And what is the best way to maintain the sparsity we have in the piecewise linear case? Multiply some of them together. That's a very good point. That's exactly what we are going to do. So if you multiply the green one with the red one, what do we get? And let's actually scale them so that they are as big as the others.
So minus x squared times.
Yes, let me use what color? The gold one. Okay. So if we multiply them together, we get 0 over here and 0 over here, because the red one is 0 here, the green one is 0 here. But after multiplication, they are going to be a quadratic function that takes the maximum value here and then goes down here. And here, because the green one is 0, the gold one also stays 0. Right? And we have another one of these on in the second element. So it stays 0 here and goes up here and back to 0 here. Now, within each element, we have a linear function goes down, a linear function goes up. The linear combination of them gives me any linear functions. And we also have a quadratic enrichment that is going to give us all possible piecewise quadratic and continuous functions. And all of these satisfy continuity requirement by default, right? Okay. Yes?
So in this way, you only have like 2 basis functions, like 2 head functions.
I have 2 head functions, yes.
But like for second order, we need a third one. So how do we construct the other one?
We need a third one?
Like for second order basis function, we need like
Oh, you mean like how did I go from these 3 basis functions to only 2 here? Is that what you're asking?
I'm kind of asking like on one element you need like for second order approximation you need like 3 basis functions.
Yes.
But here you have constructed like 2 parabola. Like you need a third to make the basis function on this element to be a second order.
Okay, so here I have 2 elements. I have 2 elements. On each element, I have the basis function is a linear combination of the green function, the red function, and the gold function. These 3 functions gives me any quadratic functions I want. Also, on the second half of the interval, I also have 3 functions: a red one, a black one, and the blue one. Right, you can't see the color very well, but like then the linear combination of them is also going to give me any quadratic functions I want. In addition to that, the gold function, the green function, red and the blue and black function, all of them satisfies continuity across the element boundary. So any linear combination of them also is going to satisfy continuity across the boundary. So right, so what I need is within each element, the linear combination of all basis functions are going to give me all possible quadratic functions. And 2, every single basis function is continuous. Then I can make sure that the linear combination of them, 1 is going to give me any piecewise quadratic function I want, and 2 being continuous.